So we have used matrices to represent graphs. So we have this adjacency matrix. And when we looked at the transitive closure problem, we suggested that it might be useful to actually describe the transitive closure computation using some operations directly on matrices. So let's look at matrix operations. In particular, we want to lead up to this notion of matrix multiplication. So a matrix in general is a two-dimensional table of values, usually numbers, right? And it has a certain number of rows because it's two dimensions. So it has rows and it has columns, right? So usually it has some R rows and some C columns. R and C could be different numbers. And we write this as R times C, or we call it an R cross C matrix. So R is the number of rows, C is the number of columns. And as usual, we will number the rows starting from 0 and the columns starting from 0. So the rows are 0, 1, 2 up to R minus 1, and the columns are 0, 1, 2 up to C minus 1. So in the example that we have been looking at, the adjacency matrix, R is actually equal to C is equal to N, which is the number of vertices in our graph. So we have one row and one column for every vertex in the graph. So we number our columns and rows as 0 to N minus 1. In this particular case, the entries in our matrix are 0 and 1, but in general there could be any numbers, even other values in general, but we will look mainly at matrices where the entries are numbers. So for a completely different example, let's consider that we want to record some information about freight traffic by rail between some cities. So let's take, say, the 6 biggest cities in India: Bangalore, Chennai, Delhi, Hyderabad, Kolkata and Mumbai. And suppose we have information about the volume of traffic, say in terms of thousands of tons or millions of tons, whatever is the appropriate metric for this, right? So we have some information, so we want to represent this as a matrix. So the first thing is that every city will correspond to an entry in the matrix in the row and the column. So because we are normally numbering our rows and columns from 0 to N minus 1 or 0 to R minus 1 and 0 to C minus 1. In this case, again, notice that it's going to be a square matrix. So it's going to have 6 rows and 6 columns. Let's just number them in alphabetical order. So 0 is Bangalore, 1 is Chennai, 2 is Delhi, 3 is Hyderabad, 4 is Kolkata and 5 is Mumbai. It does not really matter in what order we put it. Okay. So this could be the matrix, right? So this is not a symmetric matrix as they say. So there is a certain amount of traffic, say from Bangalore to Chennai, but there is a different amount of traffic from Chennai to Bangalore, because in general there is no reason why the amount of freight traffic should be the same in both directions. Notice that along the diagonal there is no freight traffic recorded from a city to itself, because that doesn't make any sense for us, right? So this is another way of using a matrix where we are representing some information about freight between pairs of cities. So now suppose we have this information and it is counted over a certain period of time. So in India, you may know that the financial year starts in April. So April 1st is the beginning of the financial year and March 31st is the end. So maybe for the first half of the financial year, from April 1 to September 30th, we have a certain amount of information about this freight volumes, and that is the matrix on the left. So this is the first one, right? So this is the first half year, and then we have a corresponding thing for the second half year. So the numbers are different. So for instance, here there's only 247, whereas here in the same entry from Bangalore to whatever was 4, right? You have Kolkata, I think, there you have 399. So now a natural thing would be to compute the freight volume for the full year, given this information about the freight volume in the first half of the year and the freight volume in the second half of the year. And quite clearly, the freight volume for any pair of cities is going to be the sum of the two, right? So if you want to know how much traffic there has been from Delhi, which is city 2, to Kolkata, which is city 4, you look up the entry for the first half of the year. It says, okay, there were 595 million tons or whatever it is from Delhi to Calcutta in the first half, and then the second half of the year was 326. So clearly put together, it was 595 plus 326, which is 921. Right? This is how we would compute this information. So some notation. So if we have a matrix, then remember our rows are numbered 0 to R minus 1 and our columns are 0 to C minus 1. So we will look at the ith row and the jth column, and that will give us one entry in the matrix, right, where the row intersects the column, and we will refer to that as mi comma j. So mi comma j is the entry in the matrix at row I and column j. So now here is our information about the 2 half years again presented on the right hand side. So these are the 2 matrices that we are given, and we want to compute the aggregate volume for the whole year into a new matrix, call it C. So I have used A for the first half year, B for the second half year, and now we want to compute a matrix C which represents the total volume for the whole year. And as we said before, the ijth entry, the entry in row I column j of C is going to be the sum of the ijth entries in A and B, right? It's quite obvious. So if you want to look at a pair of cities and find out the total traffic between the two cities, you add up what traffic was there in the first half of the year to what traffic was there in the second half of the year. So when we do this, we are doing this for every element, right? So we are taking this element, adding this element and getting this element. We're taking this element and getting this element, right? So we are doing it in the same way for every element of the matrix. And so we can just concisely say that we are adding these two matrices. So this is called matrix addition. So when we have a matrix A and a matrix B and they both have the same size, the same number of rows and the same number of columns, then for every position in A, there is a corresponding position in B. If I look at row I, j and column j in A, there is a row I and column j in B because they have the same size. And so I can now add these entries and put it into a third matrix of the same size, and I will just write C equal to A plus B. Right? So C equal to A plus B captures this fact that for every row and every column, I am adding the entries in A and B to put them into C. So remember that we were not so interested in adding matrices but multiplying them. So what should we do for multiplying matrices? Right? So can we multiply matrices the same way? So let's take simpler numbers. So here are two matrices A and B, and suppose we do the same rule, right? The same rule would say instead of adding Aij to Bij, multiply Aij by Bij, right? So here for instance, if I look at C10, it is A104 times B105. 4 times 5 is 20. Similarly, if I look at, say for instance, A32, it's 5, B32 is 4, so again it's 20. If I look at this entry, it is 9 times 4 is 36, right? So I have just multiplied entries one at a time. So this could be a candidate for the operation of matrix multiplication. It's the obvious way in which we can take addition and replace addition by multiplication. Now it turns out that this particular way of manipulating matrices, there's nothing wrong with it. It's just that it does not turn out to be very useful in practice, right? Addition actually made sense for us. Multiplication like this usually does not give us any useful number. So there is a different operation which is given the name matrix multiplication, which is a little more complicated than this, right? So we want to compute the multiplication A times B, where A and B are matrices. So again we have to tell us a rule for computing the ijth entry of the product, right? So the product of A and B has again entries I comma j. So what is the value that goes into Cij? So here is the complicated rule. The complicated rule is that you look at row I, okay? So you look at row, so this is my matrix A and my matrix B. So if I want to compute the ijth entry in C, right, I look at row I in A and I look at column j in B, right? So I look at the first entry here. What is the first entry here? It is I comma 0, and I look at the first entry there. What is the first entry there? It is row 0 column j. So I multiply those two numbers. Now I move to the right and I look at the next number here, that is I comma 1, and I look at the next number in that column, that is 1 comma j, and I multiply those two numbers. So I keep walking down the row in A, the ith row, at the same time I walk down the jth column in B, and every point I stop and I multiply the two numbers that I get. I take all these numbers and I add them up, right? This seems really complicated, but this is how matrix multiplication works. Okay, so let's do an example. So supposing I take these two matrices and I want to find out what is the final entry going to be for C13, that is row 1 column 3 of the final matrix. What is it going to be? Well, I have to look at row 1 in A, right, and I have to look at row 3 in B, and then I have to start one by one. So first I multiply 4 by 8, right? So that's my first component. Then I have 0, which is nice. 0 times 2 is 0, no problem. Then I have 9 times 1 is 9, and then I have again 7 times 0, another 0. So I get 32 and I get 9. So 32 plus 9, so I get 41, right? So this is how I compute one entry. This is just one entry, and I have to do this for every position, right? So for every position in the output, I have to scan a row of the input and a column of the second matrix, a row of the first matrix, and add up those that many. I have to multiply each individual pair and add them all up, right? So I have to do a lot of work to compute one entry, and if you do this, then you get this matrix. Okay, let's look at some other entry and see how did we get this 46, right? How did we get C11? Well, so C11 means I have to look at row 1 and I have to look at column 1, right. So I take 4 times 1 is 4, then I get 0 times 0 is 0, then I get, this is right, then I get 9 times 0 is 0, and then I get 7 times 6 is 42, right. So this is how I computed it, and then I finally got 46, right. So by any entry I can do that, right. So I can take this 54 and do the same thing, right. So I want now, if I want this one, then I want to go to the, I want to go to 2 comma 3. So I want to go to row 2 column 3, and now I have 8 times 6 is 48, plus 3 times 2 is 6, plus 0 times 1 is 0, plus 1 times 0 is 0. So I get 54, right. So this is how I compute the product, okay. So what we have described is called the matrix product, okay. So this thing on the right, by computing for every, so what we have done in particular is a square matrix. So R is n, C is n, right. So we say Cij is ai0 b0j plus ai1 b1j up to ai n minus 1, the last column, and bn minus 1j, the last row in the column j. So there is a simple way to write this in mathematics notation, which is that you replace this entire summation by the summation sign. So we say let this second position range from 0 to n minus 1. So we take the summation over all k ranging from 0 to n minus 1 of aik times bkj, right. So this is just a shortcut for writing that long sum without having to specify every term and writing dot dot dot. So in general, we don't need these matrices to be square. What we want is that this thing is well defined, right. For this thing to be well defined, when I am walking down row I in A, I must be able to take the same number of steps in column j in B. So therefore, if I look at the length of a row in A, if I process some number of elements in that row, then I must be able to find a matching element for each of them to multiply and then add up, right. So the length of a row in A must be the same as the length of a column in B. So remember that we write these things as R by C, right. So if I look at A, so it has some R1 times C1, and look at B, it has some R2 times C2, right. So what is the length of a row in a matrix? The length of a row is a number of columns, right. The number of rows is how many rows there are, but I want to know how far can I go in a row. So that is the length of a row in A is C1. What is the height of a column in B? It is the number of rows, right. I go from the top row to the bottom row. So that is R2. So what I want is that R2 is equal to C1, right. So what we are saying is that if A is m cross n, then this n must be the number of rows in B, and B can have any number of columns, okay. So we can take two matrices which have different shapes provided the number of columns in A is equal to the number of rows in B, okay. Only then I can do this summation correctly, okay. So let's look at an example. So what happens here is, supposing now I have something which is 3 times 4, right. I have 3 rows and 4 columns, and here I have 4 rows and 3 columns. So now when I take an entry here and I multiply it by an entry here, I get one entry here, right. So I get 6 times 5 30 plus 6 times 8 48 plus 3 times 2 6, which is 84, right. So I have an entry in C for every row and column which is there as a row of A and a column of B. So finally I end up with a matrix which has as many rows as A and as many columns as B, okay. So if I start with m by n and multiply it by an n by p matrix, I end up with an m by p matrix. In our context, remember that we are dealing with adjacency matrix. So in our very limited context in which we are using it for graphs, this actually doesn't matter because we are always going to do square matrices. But matrix multiplication in general does not require the matrices to be square. It only requires this correspondence between the columns of A and the rows of B. So now let's get back to the problem which motivated all this, the problem of transitive closure. So remember that transitive closure was trying to capture the fact that two vertices in a graph. So it started off with the relation. We said that we have a relation and we want to find out whether two objects in our set are related by a sequence of pairs in the relation. And then we said we will model it as a graph, and now every relational pair in our relation is modeled as an edge in the graph. So finding a sequence of relational pairs in our relation is the same as finding a sequence of edges in our graph. So it's the same as the reachability problem. So can we find out which all pairs are reachable from each other? So we started with an adjacency matrix. So this is just some arbitrary adjacency matrix. We don't really need to worry about what this graph represents, because once we have the adjacency matrix, we said we can compute directly with it. So the property that we know is that adjacency matrix captures paths of length 1. In other words, direct relationships which were already given to us in the R relation we started with. Right? So the edge relation is the relation R that we are trying to visualize. So we know all things which are directly related because that is given to us. Now we want to go from that to say things which are related indirectly in one step. So we look at what we call A squared, which is all pairs which are connected by a path of length 2. By length 2 we mean there are 2 edges. I need to traverse 2 relationships to go from I to j. And we said that if you want to go from I to j in 2 steps, that means there must be an intermediate vertex, and we call that k. So there must be some k such that I go from I to k and then I go from k to j. Right? So that was our A square. Right? So now how do we put this in the framework of matrix multiplication? That's what we are trying to do. So we are not doing multiplication addition over our normal numbers. Okay? We are doing multiplication and addition actually over the values true and false. So we are doing something which is called Boolean algebra. So let's just write it down and understand what we are doing. So remember that these things basically indicate that there is an edge. So I can write this as true. Okay, or there is no edge, this is false. Right? So this is saying that there is an edge from 0 to 4, there is not an edge from 1 to 5. So the 0 is interpreted as the non-existence of an edge. So if the answer to the question is there an edge from 1 to 5? The answer is no, false. There is no such edge. Therefore the answer is 0. And is there an edge from say 3 to 4? So the entry at 3, 4 is 1, and therefore the answer is true. So we're working with these 2 values only. So this is a 0, 1 matrix. So 0 represents false, 1 represents true. Right? So this is our starting point. And now the operations that we are interested in over Boolean values are AND and OR. Right? So if I want to say OR of 2 Boolean values is true provided at least one of them is true. So only if both of them are false is the answer false. So if I now represent this OR by plus, okay, so this is where now this matrix multiplication idea is going to come. So this is the algebra. So we are now representing the values by 0, 1. So first of all, we have removed true and false from our Boolean algebra, from our Boolean set, and we have replaced it by 1 for true and 0 for false. Now we are taking operations and replacing them by what we think of as arithmetic operations. So we are taking the logical OR, which says false or false is false, and false or any other pair gives true, by saying that, okay, if plus is OR and 0 is false, then 0 plus 0 is clearly 0. Okay, 0 plus 1 is 1, and 1 plus 0 is 1. This might even follow from the fact that they are numbers. Obviously even as integers 1 plus 0 is 1 and 0 plus 1 is 1. What is perhaps surprising from a numeric point of view is that 1 plus 1 is also 1. So clearly if we are thinking of these as integers, 1 plus 1 would be 2, but 2 is not really a value that we are dealing with. We are dealing with only true and false. So what this is saying is that true or true is equal to true. Right? So we are taking this and making it plus, we are taking this and making it 1, taking this and making it 1 and saying this is 1. Right? So this is a kind of strange kind of arithmetic we are doing, but it is justified because the underlying interpretation is in terms of logical values and logical operations. The other interesting operation for us is AND. Right? So AND is kind of symmetric to OR in the sense that in AND we need both to be true. So the only interesting case is 1 cross 1. Right? So 1 times 1 is 1. That means true and true is true. And if any of them is 0, then the answer is false. Right? So false and anything is false. So both are false or one is false, it doesn't matter. So now this is our setup. Right? So we are working with a 0, 1 matrix, and now we have these operations multiplication which represents AND, and OR which is represented by plus. Right? So now let's look at what this says. This says as for some k, so a squared ij is 1 if for some k I can find ik equal to 1 and akj equal to 1. Right? So for some k, so what are the possible values of k? K could be 0, k could be 1. So k has to be one of the vertices, right? So k could be 0, k could be 1, k could be 2, anything up to n minus 1, right? So this expression, this sentence here translates to saying either k is 0, in which case I have a10 is true and a0j is true, or I have k equal to 1, in case ai1 is true and a1j is true, and so on. Or finally, the last possibility is that it is ain-1 and an-1j. So if any of these pairs aik, akj is true, simultaneously true, then there is an edge from I to j. If more than one is true, it is still true, right? If I have multiple ways of going from I to j in 2 steps, that's still okay. I need at least one. So this is just the expression for this left hand side definition, written out using the logical operations and or, and interpreting the entries in the original adjacency matrix A as true and false. But notice that this is the expression. If we write it using this algebra here, we replace every and by times and we replace every or by plus, right? So this is our algebraic way of writing out these ands and ors. So once we have written this out using ands and ors, it is very clear that we have actually written out a matrix multiplication entry in terms of this new interpretation of ands and ors. So a squared ij is the summation of all k from 0 to n-1 aik times akj. This was exactly the equation we wrote for an arbitrary matrix product. We said Cij is a summation from k equal to 0 to n-1 of aik times bkj. Right? So that is the reason why a square is actually just in matrix terms a times a, provided we think of a as having Boolean value 0, 1, and we think of or as plus and as multiplication. Right? So using that interpretation and those rules for plus and times, we get precisely a times a. Now proceed next step in transitive closure. We look at paths of length 3, and we said a path of length 3, for instance, could break up as a path of length 2 followed by a path of length 1. Right? So I need to go from I to k in 2 steps and then from k to j in 1 step. Right? So then in the same logic, we can compute that this is the or over all k of this. So it is a summation over all k of a squared ik times a kj, because a squared captures the length 2 paths, a captures the length 1 paths. Now of course we could also decompose this length 3 path as a length 1 path from I to k and a length 2 path from k to j. It's the same thing, right? I just want to reduce the path of length 3 into 2 things I already know, either 2 plus 1 or 1 plus 2. So it could be a squared times a, it could also be a times a squared. The intermediate k could be first finding an entry in a and then finding an entry from k to j in a square. It doesn't matter. So a cubed is either a squared times a or a times a squared. Notice that here when I did a square, I didn't have an option because both are a. So it doesn't, there's only one way to decompose a 2 length path, it's 1 plus 1, right? Because that's the only information I have. But for a 3 length path, I can do 1 plus 2 or I can do 2 plus 1. Right? Now in general we said if I already knew paths of length L, then I can extend to L plus 1 by again multiplying by A, right? So I can take all paths which are pairs which are connected by a path of length L, extend it by one more thing, right? And then I get all paths of length L plus 1. So each successive length path can be got by matrix multiplication. Again, we could also invert it. We can first take one step and then take L steps. Right? And of course you could do other things also. Supposing L is 7, you could first take 3 steps and then take 4 steps, but it's convenient to write it in a uniform way so that we know how to do it systematically from 1, 2, 3 onwards. Right? So this is how we get paths of different lengths by consistently multiplying one more time by A. So we take the matrix we already have for L steps, multiply one more time by A. So each time we multiply by A, we take the matrix we have computed in the previous step and multiply one more time by A. So it's A times A times A times A. So implicitly this thing contains a lot of A times A times A in it, L times, right? So there are L times that and then one more time. So this now gives us paths of specifically of length 1, length 2, length 3 and all that. But what we said is we wanted to know whether there was a path of any length. And then we observed that of course because it's a graph, if there is a path at all, there must be a path of at most length n-1, because if it is longer than that, then there will be a loop which you can remove because there are only n vertices in the whole thing. So if I take n-1 steps starting from a vertex and each time I go to a new vertex, there are only n-1 new vertices I can go to. If I take one more step, then the next vertex must be one of the n vertices I have already seen before, and that would be useless. So therefore it's sufficient to look for this matrix of length, path lengths up to n-1. So what we want is there a path of length 1 or length 2 or length 3 or this, but each of them is represented by a matrix and OR is plus, right? And so now we can go back to matrix addition. We want for each ij, we want to check whether aij is 1 or a squared ij is 1 or a cubed ij is 1 or a4 ij is 1 dot 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 up to a n minus 1 ij is 1. We want to check if any of them is 1, and that is the same as doing plus 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 plus, right? So this is why we get the transitive closure, which we wrote as a to the power plus. Right? The transitive closure is just the sum, the matrix sum of these n minus 1 matrices. The a which is, this is really a to the power 1 implicitly. So a which is the 1 length paths, a squared which is the 2 length paths, and so on. Right? So that's how we got from transitive closure to matrix multiplication, right? By using the entries in A as Boolean values and interpreting the two operations plus and times as logical OR and logical AND. So to summarize, what we have seen is that we can take matrices and operate them as a whole, and depending on what operation we are doing, the operation is defined differently. So matrix addition is very simple. It is just defined element wise, and it tells us that the ijth entry of the final sum is the sum of the two ijth entries in the initial matrices, right? And for this we need that A and B are compatible in the sense that they have the same number of rows and the same number of columns. So then we get C is equal to A plus B. On the other hand, if we want to do a matrix multiplication, then we have to take for each entry ij in the final thing, we have to go through row I and column j of A and B, and then pairwise multiply all the terms and then add them up. So that is this summation, right? And for this we need that the number of rows, number of columns in A must be equal to the number of rows. So if I walk right some n times, then I must be able to walk down some n times. So n is the number of columns in A, it must be equal to the number of rows in B. So we have this constraint that A and B must agree on this component, the number of columns in A and the number of rows in B. And finally we end up with a matrix which has as many rows as A and as many columns as B. And then we saw that if we interpret the adjacency matrix as a Boolean matrix, the values 0 and 1 as being representing true and false, and we think of the operations AND and OR as being represented by multiplication and addition, then we can actually think of our transitive closure computation as initially doing a bunch of matrix products. So we get a to the power L plus 1 as a to the power L times A, and finally we add up all the matrices we have computed from a to the power 1, the original one, up to a to the power n minus 1, where n is the number of vertices in our graph.